the Cartan-Killing form. And now we'll, did we complete the whole chapter or not? Yeah, I think we did all of it, right? Yeah. Okay, so now let's go to the chapter 212, and now things are going to become very interesting. I mean, because we'll learn a lot about the general Lie algebras. I mean, not all the Lie algebras, what we call semi-simple simple Lie algebras. And so let me just quickly, I think I already defined, but let me just quickly repeat that again. So chapter 12. Okay. So the definitions, first definition is 12.1. We have already discussed that a simple Lie algebra, simple algebra or simple Lie algebra has no non-trivial. By non-trivial meaning proper. I mean, because not proper, right? Non-trivial ideals. You understand proper what it means? It's something which is not the full Lie algebra, neither the zero. I mean, the zero is a zero-dimensional subspace, right? Zero is just a point zero. So, no, and with the exception, we must exclude, although it's not written here in the text, but normally when one, because you see, if you take U1 theory, U1 satisfies all this condition, right? Its dimension is 1, right? And so there is no proper ideal, right? But that you don't normally call a simple Lie algebra. So except for U1. Because U1 satisfies this condition, but it's not called simple. U1 is just a triviality. So everything higher than one dimension. This is one-dimensional algebra, right? Everything higher than one-dimensional algebra, which has no non-trivial ideal, is called a simple Lie algebra. Then 12.2, and this is interesting. I mean, this will not prove, but so there are, okay, so the way we, in these notes we proceed is that we use this as a definition, okay? So this definition says that a so a Lie algebra is semi-simple. A Lie algebra is semi-simple, is called semi-simple if the Cartan-Killing form, I just write short form B is non-degenerate. Non-degenerate means the determinant of the B is not 0, so that B inverse exists. Okay, that's what means non-degenerate. Then from this one can prove, and we'll not go through this proof now. I mean, if there is some extra time left towards the end of the course, I mean next week, then I can go back if you have questions about this. But I will just state this theorem that so the Lie algebra, I mean, is written 12.1 theorem. It just says that Lie algebra is semi-simple if and only if so both ways, if and only if it has no abelian ideals. Usually in the mathematics literature, they use this as a definition, okay, or the semi-simple, and then prove this theorem, prove this as a theorem, starting from here. But these two statements are equivalent, so you can just equally use this as a definition, and then of course one should prove this. But I'm not going to prove that. It's not very difficult, but let me not waste time on. I mean, let me not spend time on that because there are too many things to do now, and we don't have much time. We use this as a definition because it is this thing, it is this criterion of the semi-simple that is what gives us a very, very powerful tool to analyze the general structure of the Lie algebra. Okay, so we use this as a definition. Okay, then a consequence of this, I mean, one can also, this again, we don't prove here, the theorem 12.2. Okay. I mean, so you see this, the difference between what is simple and semi-simple. Semi-simple should not have any abelian ideals, right? But it can have non-abelian ideals. There's no problem with that. Okay. Whereas simple has no ideals at all. So here the statement is not about just abelian ideals, any ideals. So it also doesn't have proper. I mean, even a proper non-abelian ideals it doesn't have. So that's the difference. So from these two definitions, one can kind of guess that semi-simple algebras can be written as sums of simple algebras. And indeed, that's what the case happens. So the statement is that semi-simple Lie algebras, I will drop Lie, because anyway we understand that it's all Lie algebra anyway. Semi-simple algebra is the direct sum, and that's important. I just underline that. Direct sum of simple Lie algebras. Okay. The direct is important. Well, basically it is. First of all, you see from this you can already see. From this already you can see the semi-simple cannot be a abelian algebra, right? It cannot be an abelian algebra because if for an abelian algebra the B is in fact identically 0. I mean, right? Because adjoint. Suppose I have an abelian algebra, completely abelian. Huh? Then if you look at add x, where x belongs to this algebra, x is an element of algebra, then add x is identically 0. Because take any y in the Lie algebra, let's say G, y belonging to G, then x with y, that is how you define add x, acting on y, right? This is equal to that, but that's equal to 0, right? So add x is identically 0 for any x. So, and the B itself is given as a trace, B of xy is a trace of add x, add y. So each of these matrices is 0 matrix. So B is identically 0. Okay. So I mean, yeah. So from this definition, you see that since we are saying that B is not degenerate, so in particular, of course, it cannot be 0 identically, right? So this cannot be abelian. But I mean, you might imagine that perhaps there is a situation like we discussed the example of the Poincare algebra, right? In the Poincare algebra, we had Poincare. I mean, that one doesn't have to go into Poincare, just even Euclidean rotation and translations. Euclidean group, one can talk about that. In the Poincare, you had the Lorentz and translations. And we saw that this was a subalgebra, okay, and it was an abelian subalgebra. So now you can you see that will not be semi-simple, because semi-simple says that it has no. I mean, this definition says it has no abelian ideals. Okay, whereas this translation, it was an ideal, was an abelian ideal. Okay. So this is not a semi-simple algebra, right? And indeed here, this algebra can be written as the Lorentz algebra with a semi-direct sum. Semi-direct, not the direct sum. I don't know how to write it. There must be some symbol for that, but I will just write it, semi-direct sum with the translation. Or in the level of group, you say Lorentz group, times but semi-direct product. Semi-direct product. Or there will be a translation group. Right? So, but that's not a contradiction of this theorem. Because what this theorem is saying that any semi-simple Lie algebra is always a direct sum of simple algebras. Not a semi-direct sum. Direct sum. Huh? That's not a contradiction because this algebra was not semi-simple. And but, I mean, okay, these things. As I said, if we get some time, we can go over it. But basically, the idea is that the way you prove it's a direct sum is by using the fact that the B is non-degenerate. So you can write down the inverses, and you can decompose your subspaces into orthogonal components with respect to this metric, in such a way that each of them becomes, it becomes a direct sums, and they are simple algebras. So this is the basic idea. But I will postpone it. In case we get some time towards the end. Okay. Now, so now we are ready to discuss we already discussed the real algebras versus complex algebras, no? And how you, starting from the complex Lie algebra, you can take different real sections and you get different algebras. So this, I will move on. And so now we start, okay, so what we'll do in this discussion, because of this theorem, right? This theorem, since semi-simple algebras are direct sums of simple Lie algebras, if we learn everything about simple Lie algebras, then we have learned everything about semi-simple Lie algebras. Because you just take those simple algebras and take direct sums, and you get the semi-simple, right? So therefore, we'll be focusing on this part, on the simple Lie algebras. Although many of the discussions we'll be doing is also true for semi-simple. Okay, it's not, but our main focus is simple Lie algebras. Okay, so first of all, let us describe. So in this analysis, as we have seen already in the analysis of SU2 and SU3, etc., a very crucial role is played by the Cartan subalgebra, right? You always write the algebra as the maximally commuting abelian subalgebra, which is the Cartan, which we call Cartan subalgebra, and then look at the remaining guys. And then remaining guys you write in terms of eigenstrings, right? Root spaces. So this is the basic technique to follow in general. So first of all, I said before already that Cartan subalgebra, you have to be a little technical. I mean, for SU2 and SU3, we have explicit matrices, so we know we can, but now we are talking in general. We don't know anything about those Lie algebras, right? So we want to deduce, our aim is to deduce just basically from this, that B is non-degenerate. This plays such an important role, as we will see in these theorems, from this we will basically deduce the entire structure of the Lie algebra, generically. This is what is most interesting. So for this we need to discuss the Cartan subalgebra. So that is definition 12.3. So the Cartan so let's say G is the semi-simple or simple Lie algebra, semi-simple. So which means B is not 0. B is not degenerate. B on this space is not degenerate. Semi-simple algebra. And H is the Cartan subalgebra. H, I don't know how should I call it like that. H is the Cartan subalgebra. It is a maximal commuting algebra, subalgebra, but one has to be a little bit more careful in how you define it. So this definition one has to. I give you an example. Maybe already from. Let's see from. Okay. Okay. Let me just say the following. So first of all, I need to define what is a regular element. There is a definition of regular element. Regular element. So what's the definition of that? So a regular element H is defined as the following way, that adjoint of H has minimum number of zero eigenstates, eigenvalues, number of zero eigenvalues. So a regular element of the Lie algebra G, so some element H, is called regular if a joint of H has the minimum number of zero eigenstates. Okay, this is a now to give you an example. I mean, so for example, if you in the SU3 itself, right? If you had done something like the following, we had. I erased this, but did you have any questions on this part? No? So if you consider this, we always took the Cartan subalgebra to be 1 minus 1 0, H1 we called H1, and H2 as 0 1 minus 1. Okay, so this space. I mean, of course, these are the basis. And then so basically all the diagonal generators, right? But what if I had taken Y? And indeed, you see, both are regular elements. It has only, both of them have only one. I mean, in the adjoint action, if you look at the adjoint action, the H1 has only two zero eigenstates, right? I mean, H1 has how many eigenstates? Zero eigenstates. It has H1, H2, of course, right? And what else? Adjoint of H1. I'm talking about adjoint H1. Okay. What else will have zero? I mean, I think there's nothing else, right? Nothing else. Because remember, the roots were alpha 1 was for AH, alpha 1 of AH1 plus BH2 was 2A minus B. Alpha 2 of the same thing was minus A plus 2B. And alpha 3 of this was A plus B. Right? So you see that H1, if you just set B equal to 0, none of this is 0, right? So none of the eigenvalues are 0 for the non-zero roots. So this was all. On the other hand, if you take Y, the combination which we are calling Y, 1, 1, minus 2, 1 over root 3, that's not important. Right? So if you look at this, then with respect to this, of course you have both H1 and H2 commuting with that, so that they are in zero eigenstates. But also you have X plus minus alpha 1. I mean, I think if you remember the diagram that we had drawn in the plot, this was the H1 eigenvalues, this was the Y eigenvalue, right? And here we had alpha 1. Alpha 1 was here, right? So you see, this is zero component in the Y direction. So both X and also minus alpha 1. These both of them had zero eigenvalue with respect to Y. So actually there are four zero eigenstates of Y. So Y is not a regular element, right, according to that definition. Whereas H1 and similarly H2 are regular elements. That's the. It is important to distinguish this because, I mean, you see, if you don't include this definition, so the definition of Cartan subalgebra now, okay, this is the definition of regular element. So Cartan subalgebra is defined, as a maximal abelian subalgebra that contains, and this is important, that contains at least one regular element. This is important. One regular element. Yeah? So at least one of these, I mean, inside this Cartan subalgebra, at least there is one element which has a minimal number of zero eigenstates. This is important because, I mean, suppose, I mean, how do you construct how do you think of it, given an algebra, how do you start constructing a abelian subalgebra? You take an element, right? And then you start asking the question, what are all the other elements which can commute with that element, right? then you take one of those which commutes with that, add it, right? And then you ask, what are all the elements which commutes with both of them, right? This way, gradually you start making it, since the algebra is finite dimensional, by in finite amount of time you'll arrive at the maximal subalgebra, right? This is what you will do practically. But suppose instead of, so if I had started with the H1, right? If I was lucky and I chose my first element to be H1, okay, then this process will just lead you to H1 and H2. That's all. I mean, a linear combination of H1 and H2. Nothing else. There is no other possibility. Because none of the non-zero roots commute with H1, right? So if you were lucky, you chose the right element, right? But suppose you had started with a Y, and this is not a regular element now, right? If you had started with a Y, you have all these guys which commute with Y, okay? Now it's a matter of luck. Okay, if you choose H1, fine, then you get back the original Cartan subalgebra, because Y is just a combination of H1 and H2, right? So if you had picked either H1 or H2 to add to that to construct your Cartan subalgebra, you are fine. But what if by mistake you choose one of these? Suppose I choose Y and X alpha 1. Now this will be your Cartan subalgebra. Because to this now I cannot add anything. Because I cannot put H1 and H2 because they don't commute with this, right? I cannot put X minus alpha 1 because that doesn't commute with that, right? So this is it. However, this will create huge. I mean, you cannot continue the entire analysis because remember what was Y. Y was okay. Y was that, but X alpha 1 is this one. 1 0 is an upper triangular matrix. And you will see that if you try to start constructing the roots, etc., with respect to this Cartan subalgebra, you will soon run into trouble. This is the reason for demanding that at least the one element is regular. In this case, both the elements are not regular. Because X alpha 1 commutes with what elements? X alpha 1 commutes with, of course, the Y, X alpha 1 itself. It doesn't commute with X minus alpha 1, but it commutes with X alpha 3, right? This alpha 3, because alpha 3, alpha 1 commute, because there's nothing out here, right? So it commutes with X alpha 3, and it also commutes with X minus alpha 2. So it commutes with 4 guys. So in this space, there is no regular element. So this is not a good Cartan subalgebra, right? So the purpose of this whole thing is to arrive at a situation where you come up with a proper Cartan subalgebra. I mean, correct Cartan subalgebra. Then you can proceed with everything else. So this is the idea. Okay. I mean, for example, if you had chosen this guy, you wouldn't even be able to find the eigenstates of X alpha 1. Add X alpha 1. No? Because as you saw, I mean, if I add X alpha, any alpha, acting on some X beta, this will give me some element X alpha plus beta, right? So it is never going to be an eigenstate. So to hide an eigenstate, this should be proportional to that, no? But that's never going to be. So with this choice of Cartan subalgebra, you wouldn't even be able to start the process. So it's just for that. Yeah. Okay. So now we arrive at a set of theorems. So we are now going to assume that we have found a good Cartan subalgebra which satisfies all this property, that there's a regular element and so on and so forth. Okay. So now the thing is, so there are several statements. So theorem, 12.3. So the first statement of the theorem, the 12.3, first statement of the theorem is that the full algebra G is a is a sum, as a vector space it's a sum of H, the Cartan subalgebra, plus the various root spaces. So I will call them G beta, right? Where beta is a sum all the roots. So so that's the first statement. The second statement is that if alpha and beta belongs to the set of roots, delta denotes the set of roots, set of all roots. Okay, that's just a notation, the set of all roots. Then, this we have already seen before. Then G alpha, G beta is contained in G alpha plus beta. That is, we have seen already. I mean, the commutator of some element x alpha with x beta is going to be some x alpha plus beta, right? And that is just obtained by, okay, that we have seen. Third, alpha, if alpha beta belongs to delta, okay, and alpha plus beta is not equal to 0, alpha plus beta is not equal to 0, then the killing form B between G alpha and G beta is equal to 0. Okay. I'm just first writing all the statements, and then fourth. Cartan killing form B restricted on the Cartan subalgebra. So this is the full Cartan killing form, right? Killing metric. But now you restrict that to just the Cartan subalgebra. Okay. So in a smaller space, you restrict it. And that the statement is that this is non-degenerate. Non-degenerate. So there are several theorems. You know, all these theorems are there. I mean, by going step by step, what we are going to do is we will finally learn what is the most general Lie algebra. You can simple Lie algebra you can write down. That is what the aim of these theorems are. And then, so then the fifth point is that if alpha belongs to delta, then minus alpha also belongs to delta. Okay, we saw that in SU3 and so on, but now what we want to do is to prove generally that this has to be the case. There's no other alternative. And then the last one, that alpha belong, the set alpha belong to delta, the set spans star H, the dual space. So you saw that in the SU3 case, the roots were alpha 1 was here, alpha 2 was here, and so on, right? Now, this is the roots, this is the dual vector space, right? They are drawing the eigenvalues in the dual vector space. As we know, the Cartan subalgebra was two-dimensional in SU3 case, right? The dual vector space to the Cartan would be also two-dimensional. So this is two-dimensional. And indeed, you see that these two are spanning the entire two-dimensional space. Suppose it had not been the case. Suppose it had been like that. All the non-zero roots were just in one direction. This and that. In one direction. No? All the roots. Okay. Then there is no way, they are not going to span the two-dimensional space. Right? So this is what the statement here is, that it is guaranteed. It is not just an accident that this happened in SU3, but this is going to happen every time. We are talking about a simple Lie algebra. So it can span the entire thing. If the Cartan subalgebra is, say, d-dimensional, then the dual vector space is d-dimensional. And what we are saying is that the set of roots, actually, by taking suitable linear combination set of roots, you can produce an arbitrary d-dimensional vector. Okay? And that's what one is saying. Okay, so let's start through the proof. I think the first two are essentially, we have already seen this before. Yeah, so the first steps are simply the first step thing is just that H, this is a maximally abelian subalgebra, so you can simultaneously diagonalize it. Okay. So you can find simultaneous eigenstates of this. And this is where, I mean, this is a bit simplified version of the proof. I told you some examples where there is a problem. Like if you had chosen X alpha as part of your Cartan, you simply cannot even find an eigenstate. So, but with that technical addition to that definition, that there is at least one regular element, in the, that's how you define the Cartan subalgebra, this happens to be true. Okay, it's a little subtle, I'm not going through the proof, it's a bit more technical. So what the statement is that all the H's, all the H belonging to H can be, I mean, one can find eigenstates can be simultaneously diagonalized. I mean, add at that. For all add H can be simultaneously diagonalized. So then it immediately follows that we can write this the full Lie algebra as a H, which is of course the zero eigenstates, right? I mean they are commutes, so zero eigenstates, and the non-zero eigenstates, right? Which are labeled by beta. Okay, so beta is of course some. There are several eigenvalues, right? If this, as we said, if this is a d-dimensional, you can choose a basis or DHS. No, you can choose a basis H1, H2, etc. H1, H2 up to HD, and then you can simultaneously diagonalize them. So the eigenvalues, this beta actually, this will have an eigenvalue. Let's say beta 1, this is beta 2, beta 3, beta d. So it will be d set of numbers. Okay, it will be vector. It will be a dual vector in the dual space, of course. So anyway, you can split your full space in terms of the eigenspaces. Okay, that's all I'm saying. This part is straightforward.
Why do we put a beta on the side?
Sorry?
Why is there a beta?
Some over beta. Because I mean there are different eigenvectors. No? Like in SU3, it would be G alpha 1 plus G alpha plus G minus alpha 1 plus G alpha 2, you know, I, summed over I.
All alphas are vectors, this set of numbers, and we have set of alphas too.
Yeah. So for each alpha, there is a space, right? The eigenspace. And the full G is a sum of all these, direct sum of all these vector spaces, sub-vector spaces. Yeah, that's right. Yeah, sorry, this notation just means summing over all the betas. So this beta belonging to delta. Beta belonging to all the beta. The non-zero roots. Because the zero root is already included there. So beta is, with beta not equal to 0. This part also we have seen already. I mean, that's simply the matter of using the Jacobi identity, which we have seen already, right? That if you take, so if you look at add H acting on G alpha. But by the way, this notation, you see, I mean, you are used to seeing an element here and another element here. But by this is kind of a notation which just says that take an arbitrary element from this space, take an arbitrary element from this space, and look at the commutator. And that, what this equation is saying, that no matter which element you take from here, and take the commutation relation, you are going to get an element inside there. That is. So if I take, let's say, add some x alpha, which is in that space, and x beta in this space. So this is in G alpha, and this is in G beta. Okay. Then you want to show that this guy belongs to alpha plus beta space, right? Which means that this must have an eigenvalue alpha plus beta, right? And that you see just by Jacobi identity, because this is nothing else but H x alpha x beta, which is, by using Jacobi identity, the same as H x alpha x beta plus x alpha. This we have done it many times, but I'm just repeating it because it's quite an important thing. This is just a Jacobi identity. So here I just use the Jacobi identity. And then once you have here, then this becomes alpha h times x alpha. So that is the x alpha, x beta, plus beta. This one is beta h. Beta h is number, so I can take it out. And then you have again x alpha, x beta. Okay. So just it's edited. So the eigenvalue becomes, this is the same. So the eigenvalue becomes alpha h plus beta h. Okay. So that's what you mean by that, g of alpha plus beta. So this was this we have seen before. So the non-trivial things are going to be now, right? This is an exercise. This is an exercise, but again I will have to do it because many of the future results are using this result. Huh? I mean, there are two ways. Either I assume that you will do it. No, it's not good. Not good. No, I will. I mean, so I'll do it anyway. So now let's look at the third. Okay, this is. So I mean, we already saw this, right? G alpha, G beta. So now let's look at some x alpha. So what is it theorem here? That yeah. Okay, so that's what we want to say, right? Alpha plus beta not equal to 0? Sorry. Alpha plus beta, okay, good. So you see, so this is exactly what we did before. So let's look at, let's try to write down the matrix. I mean, think about this. I mean, that's one way to do it. Add of some x alpha. So let's suppose x alpha belongs to G alpha. Okay. Now, if you look at the way this will work, so you will have so this will take maybe better to do it the same way. So x alpha will take x beta to x alpha plus beta, right? Some x alpha plus beta. Right? That's what this equation is saying. I mean, this is nothing else but add x alpha acting on x beta. That gives you some x alpha plus beta. Okay. So let me just call it gamma. Gamma gives you x alpha plus gamma. Okay. Now let's apply now add x beta on this object. Okay. That's going to be the same as add. That's going to be the same as add x beta acting on x alpha plus gamma. Alpha plus gamma. Okay. But now again use the same rule. So what will be this? This will be x alpha plus beta plus gamma. Okay. Now suppose I have to write this thing. The trace is defined by using some kind of writing it as a matrix, right? So in writing a matrix, let's use this basis. So you have the same basis. You have G here. H here. Then G alpha, I mean G gamma for various gammas. So so G gamma 1, G gamma 2, etc., etc. Okay, choose the basis like that. So arrange all the first whatever the dimension is. Suppose this is dimension D. D of the first D elements are in the matrix are the elements of the karma. Then the next, whatever the dimension of this space is, that many for the G gamma 1, and so on. Right? So in this basis, now look at what is this combination, this combined action. So if I look at now add x beta, sorry, add this product, add x beta times add x gamma, x alpha. So how we saw that the product of these two guys takes x gamma to x alpha plus beta plus gamma, right? So this acting on H will take you to G alpha plus beta. This acting on that will take you to G gamma 1 plus alpha plus beta, right? And on this gamma 2 plus alpha plus beta. So there is no diagonal term, right? So I mean, so you see, I mean, let me write like that. Gamma here, and this is gamma plus alpha plus beta, etc., etc., right? So if alpha plus beta is not 0, if this is not equal to 0, then you see these two spaces are distinct spaces. They have different eigenstates, right? And in that, so how will this look like, this matrix? This matrix will look in this way, if I write it in these block forms. So this was the H, and this was the kappa, this was G gamma, this is G gamma plus alpha plus beta, and so on. And here you have H, G gamma, and G gamma plus, I mean, just to remember what here. So then you see in this notation, this will be non-zero only, I mean, if I look at the G gamma part, here it will be non-zero only here, and here, no, here actually. There will be no diagonal term, that's what I'm trying to say. For diagonal term to happen, this action should give you back again something in the same block, right? But that can only happen if alpha plus beta equal to 0. If alpha plus beta is not equal to 0, it is completely off diagonal. So when you take the trace, it will be 0. And the B was defined as a trace of these two, product of these two, right? So the trace is going to be 0. That's a statement. Is that clear? I mean, because for trace to be non-zero, the action of this guy should take a particular state and bring you back to the same state. No? Otherwise, there will be no diagonal entry. Okay. Yeah. I mean, something here will be non-zero. Similarly, there will be another space. I didn't write. Not here. Sorry. The G gamma. So this will be non-zero. For the H, there will be also G alpha plus beta. If alpha plus beta is a root, then there will be also such a space. And this H guy will be taken to that, right? I mean, this was finally going to. So the combination add X beta and X alpha acting on X gamma was ending up in the space some X gamma plus alpha plus beta. That's what it's saying. So, so if you take gamma equal to 0, which means 0 root, that is H itself, right? H will go to X of, I mean, gamma is 0, so X of alpha plus beta. So this will be G alpha plus beta. So an element of the H will be taken to the element G alpha plus beta. So every entry will be off diagonal. That is why so trace will vanish. It's not that the matrix vanishes, the product vanishes, but it's a trace that vanishes. And the trace is how you define the metric. So trace vanishes, implies trace of this guy equal to 0. If alpha plus beta is not equal to 0. If alpha plus beta equal to 0, there is no problem. Right? Because then it's a diagonal. I mean, X gamma will go to X gamma if this was 0. Right? In that case, then you cannot say a priori whether trace is 0 or not. No? But if this was not 0, alpha plus beta is not 0, then you know for sure trace is 0. Right? That's a statement. Okay, this is basically the statement here. Now the fourth one, right? So this is the statement, the BG alpha. This is nothing else but the trace of add X alpha, add X beta for arbitrary elements of X alpha from here and X beta from there. Now this is so now we want to show that if you restrict B to H, the Cartesian algebra, it is non-degenerate. Right? So let us say again in this basis, how will add H look like? Let's look at that basis. I should erase that. So add H. So if I look at now add H, and I write it in this basis. So you have H, and then G alpha, and so on, right? So no, actually we already used it. So this tells me, first of all, this tells me that B, I mean already the statement number 3, the 3 implies that B of H with any G alpha is 0, right? So where alpha is not 0. So H belongs to, so X alpha, let's say. X belongs to the H, the Cartan subalgebra, and X alpha belongs to some G alpha, where alpha is some root which exists in the Then this is 0 by the same argument, right? Because we are saying that by the only time it may be non-zero is if alpha plus beta equal to 0. But here, H means it's beta equal to 0, right? Okay. Is that clear? Is that point clear? No? I mean, just specialize it. Just specialize it to take the statement for beta equal to 0. Just take beta equal to 0. Then you get, well, this certainly, alpha is already starting. To start with, I'm saying alpha is not 0. So alpha is not 0 here. And then this tells me it is 0. So the only way the B of any H can be non-zero is if this guy was in the Cartan itself, right? Otherwise it's 0. But the assumption that B is non-singular, what does it mean? Well, I mean, you know that at the level of linear algebra, what it means to say some matrix is non-singular. It has inverse exists. It's a statement that, I mean, if I take an arbitrary, so non-singularity of B, non-singularity of B means that for any arbitrary element, let's say X, for any arbitrary element, X could be in the Cartan or anywhere, it doesn't matter. For any arbitrary element, for any B of X with Y cannot be 0 for all Y. Okay? I mean, fix an X, take an X, and start varying or take all the possible Y's. It cannot be that this is equal to 0 for all possible Y's. It may be 0 for some of the Y's, right? But not all possible. Because if it is 0 for all the Y's, then, and this X is a non-trivial element, it's not a 0 element, okay? Then you cannot invert the matrix, right? This you can easily see by choosing a basis, okay? By choosing a basis for this, choose some basis, let's say yi are some basis, yi are basis, I equal to 1 up to whatever the dimension of the group is, the Lie algebra is, or the vector space is. So you have chosen a basis, and if this is true for all I, okay, then you see that you cannot, then you cannot invert it. You cannot invert the B. No? Is that clear?
Can you find by calculating B of H and X alpha, or X alpha and X alpha 2, can you write the matrix form of the B in terms of that basis we are using them?
B of what?
For example, that BH X alpha is 0, is it like the entry of the matrix, like the...
Yeah, I mean, in fact, you can see that already from here. This is like exactly the, I mean, I'm using just this statement, right? But this statement is following from this representation, this writing it this way. Right? So H, if you look at the add H action, add X alpha, it will just be off diagonal elements, right? Add H with, I mean, this object, add H times add X alpha, is going to be purely off diagonal.
Yes, but to find all entries in that matrix, we can use not that matrix, but the matrix for B. For example, if I want to see B in the matrix form, I can calculate all possible H, X alpha, X beta, all possible dot products between them, and possibly write the matrix for B.
Yeah. You can do that. I mean, that is just saying that, like, you can choose a basis and write down the B as a matrix, right? Yeah. You can do that. I mean, if you choose a basis, so if I have all these bases, I can write B, yi, take B, yi, yj, and call this some number. This some number, call this bij. Okay? Then this will be a d by d, I mean, this will be the components of a d by d matrix.
So now we are saying that if this is satisfied, the bij matrix has determinant.
Yeah, you can see that. Suppose, I mean, x, since yi is a basis, okay, maybe I should just say a little bit, write it. Yeah, I understand your question, yeah. Because I thought you were referring to this part. No, no, okay. Okay. So there's, yeah, to really see this, one can see the following way. Well, x, since y is a basis, I can always write it as some ai, yi, right? Some lower I. Any vector x I can write like that. And since I'm saying it is non-zero, then not all the ai's are zero. Okay. Now if I plug it that here, so then I will get b of x, yi, yj, let's say, equal to, I can plug that here, it will be just ai, b, yi, yj, right? Which is, from that, I mean, I'm just calling this, which is simply ai, bij, right? And we are saying that this is equal to 0 for all j. So now you see that this is a matrix equation. I can write it as a matrix equation. B, A, so B, I, A, I, A, right, is A1, A2, A, D. Let's say D is a dimension. And write it as B, the matrix B. You see I'm writing this B matrix. So B1, 1, etc., etc. And that's equal to, we are saying is 0, 0, 0. Everything is 0, 0. Right? That is what this is. I mean, if it was the case that it was 0 everywhere, we want to show that this cannot be happen, right? This cannot happen. So if you look at that, then if the inverse exists, that would imply that all of those guys are 0, right? Because you can multiply by the inverse. Then this will be equal to 0, 0, 0 times the B inverse. Okay. But so 0 multiplied by anything is 0. So then it would imply that the only time this can happen is when all of these guys are 0, which means x is a 0 vector. So this is the statement. Exactly. So these are, I mean, I don't know how much experience you have with the linear algebra. This you can go back and forth between these concepts. No, one way to say is that determinant is not 0. Right? Another way to say, equivalent way to say is that there exists no non-zero x such that it is b of x with arbitrary element is equal to 0. No? There should be at least some element here for which it is not 0. Otherwise, there's a contradiction. Right. So, yeah, what was that? So therefore, so now going back here, b of h with x alpha is 0, right? That I know already, for alpha not equal to 0. So the only possible place where this is not 0 is if this guy is also in the Cartan subalgebra, right? So the B, if I write down the B matrix in this basis, the B. So B, I write it in this basis here, H and G alpha, etc., etc. And then the HH component of that can only be here. Everywhere else it is 0. Right? Because we are saying that B of H with X alpha is 0. Right? So if I write B as a matrix in this thing, where I mean all these basis vectors I'm choosing Y's. So some first few basis vectors I choose for H. The next basis vectors I choose for G alpha, and so on and so forth, right? So I can arrange in this basis, Then we see that the only I'm not saying anything about this part. I'm just saying that this part and that part, here everything is 0, here everything is 0. Okay? So the only possibility is here. This is the only thing which may not be 0. May or may not be 0, right? But now if I look at the determinant of this matrix, you remember, for B inverse to exist, the determinant must be non-zero. The determinant of this will become determinant of this times determinant of that, right? So so therefore this determinant must not be 0. So that is a statement here, that the B restricted to H is not degenerate. So this part itself has non-zero determinant. I mean, this you could not have said without proving that these guys are 0. Because if this was not 0, for example, then the full determinant is not just the determinant of this times the determinant of that. No? You see, I mean, suppose this was not 0, this was not 0. Then it is not true that the determinant of B is this determinant times that determinant. That's not true because there are cross terms. No? But we, from this statement, we are saying that all of these guys are 0. These are the components which are of this type. B of H with X alpha. They are all 0. So, okay, so that is this statement, that non-degenerate. And then, yeah, and also from this, again, it follows the same argument. The next one is exactly the same. Because, I mean, so we already said that B of X alpha with X beta is equal to 0 if alpha plus beta is not equal to 0. Right? This was, I think, that statement there. This statement here, third, number 3. Okay? So that, I mean, it means, so pick an X alpha, then there must be, I mean, the only, you see, this argument is telling me that if I choose any element, I mean, if it's non-degenerate, if I choose any non-zero element, then there must exist some element here such that B is not 0, right? But on the other hand, so which element can be non-zero? The only possibility is X minus alpha, right? That's the only time when this condition is not, I mean, this plus that is 0, right? For anything else, for any other beta, this would not satisfy that condition, and therefore it will be 0, right? And since I know there must be some element with which Bx alpha is not 0, then that element has to be X minus alpha, right? So that tells you that there must exist a minus alpha root. If there was no minus alpha root, then there won't be any such term. This will not be there at all. This wouldn't exist, right? And then we will conclude that X alpha with X alpha is orthogonal to everything else, orthogonal with respect to this metric. It will be orthogonal to everything else. So, no. Including itself.
So like this calculation refers to the diagonal terms on the.
Sorry?
This calculation X alpha X minus alpha refers to the diagonal terms on the.
Yeah, it will be of the form, I mean, so if I write this basis, so you have a G alpha and G minus alpha, right? Then the B will go like, so this will be non-zero, this will be non-zero, this will be 0. So determinant is not 0.
Both diagonals on the diagonal boxes.
Yeah. So each block, alpha minus alpha, say beta minus beta, so those blocks will be like that. So this was the alpha minus alpha block. Similarly, there will be beta minus beta block, and so on. And the determinant will not be 0. Yeah. Actually, yeah, from this also one can conclude many things. I mean, that the dimension of this must be the same as the dimension of that, and so on. Right? There are many powerful things we can conclude from just a non-degeneracy of this. Okay. Then the fifth point, yeah, we said alpha belongs to that. And yeah, this point, alpha, yeah, the last statement which I have erased here. So the fifth was that minus alpha, if alpha belongs to delta, implies that minus alpha also belongs to delta. That was that last statement. Right? Otherwise, it will be degenerate. And finally, we want to look at the last statement. So the sixth point was that alpha belonging to delta spans, so this set spans H star, the dual vector space. Okay. So the way to prove is that yeah. So the idea is the following. So, I mean, what does it mean to say it does not span H star? Well, the dual space was something like this, right? Any, I don't know, let's call it, so we have, so dual vector spaces, you remember I told you, is just the set of linear functions, the space of linear functions, right? On the original vector space. So, a set of linear functions are, I mean, if I recall the original vector space as the components in some basis as xn, okay, or choose some basis, then I can define any linear function as any linear function of x as x is in some basis, let's say, as some ai or fi xi, right? Summed over I. So this fi will span so arbitrary fi's will span the dual vector space. So this again is the same dimensionality, right? This index I. But if suppose it doesn't span, then there must be some linear function which is zero completely on arbitrary, right? You understand what I'm saying? I mean, suppose it didn't span all of it. Okay. Then there exists. So if alphas, if they do not span, if alphas do not span H star, then there must exist some H belonging to H such that alpha H equal to 0 for all alpha. So remember, alpha is a set of linear functions, right? So think of this way. So there is some, so alpha, so for, I mean, there's some, how to put it? So let's say H is some three-dimensional space. So we are saying alpha doesn't span everything. So H star must be also three-dimensional space, right? If you are saying it doesn't span everything, say suppose it spans only two-dimensional subspace, right? Then there is some other direction. So some other guy which is giving you 0 with everything else, right? That is what I'm saying. So there must be, so let's say I have a space here which is a three-dimensional space in the H. Okay? Whereas in H star again I have a three-dimensional space. But alphas are only spanning this part. Okay? So that's what we are saying, right? Suppose alpha doesn't span everything. So let's take an example. Alpha is spanning only this, right? Then, since this is not covered, and you see, so therefore there must be some H. So some H, let's say, suppose I choose my basis in such a way that this guy gives non-zero only with that. Okay, this guy gives non-zero only with that. This guy, this direction gives non-zero only with that. Like I'm choosing this basis, fi, xi. Okay. So in this basis, then if I take any H which is in this direction, okay, that is going to be orthogonal to all of these alphas, right? So that's the statement. That there must exist some element here, okay, which is giving 0 with every alpha. Otherwise, if it was not, suppose for arbitrary H, alpha H was not equal to 0, then alpha is spanning, by definition, alpha is spanning the entire dual space. Okay. So this is a statement. So therefore, there must exist some alpha H so that it is.
Actually, for example, if it won't be 0 for any alpha, you can have. We know how alpha x of H1, H2, and H3 being the basis of the H. We also need to show that there must at least 3 linearly independent alphas that can span.
Yeah, exactly. So
I mean, is this condition enough to say that they span? Shouldn't we need to look for linear combinations of the dimension of H, number of A's? There is only possibility to.
Yeah, I mean that's what I'm saying. The H is this is an arbitrary element here, right? I mean the Cartan subalgebra is an arbitrary element. So we are saying that, I mean, if it was true that for any H, right, the alpha H is alpha H is not equal to 0 for all alpha. Then we are spanning everything. Then we are spanning.
Is this enough to say that?
Yeah. This would.
I mean, maybe there are two kinds of alphas that act proportionally to all H's.
But then it is not. Then it's not spanning, right?
Yeah, but they would satisfy this statement.
No, so go back here. I mean, in this example of SU3. I mean, this example. Suppose everything was pointing in one direction.
Yes.
Right. Then there, I mean, there are H's which exist.
And then there is always an H which gives 0.
Yeah, which will give you 0. Exactly. That's what I'm saying. So there must exist, if any H exists such that for all the alpha it is equal to 0, or take combinations, yeah, sure, take any linear combinations, then this is...
so we can always find an orthogonal
direction
to constant.
Yeah. Like here, I'm choosing a basis. Choose a basis and choose a basis for this is the basis for the dual space, right? So, yeah. But then we'll run into a contradiction. Okay, so we are saying that, let's just suppose it doesn't span, so we are proving this by contradiction. Okay. So we are saying suppose alphas do not span H star, then this implies there must exist an H such that this is true for all alpha. Okay. On the other hand, you have seen, this was I think we saw yesterday, BHK, where H belongs to, or H and H prime, let's say. This, both of them belong to, H and H prime belong to H. This was nothing else but sum over alpha I H, alpha I H prime, where alpha I run over all roots, all the roots. Then this we saw, right, yesterday, you remember? Yeah. Okay, so now so take this H to be that H, okay, for which all the alpha H's are 0. Okay. Then you see that H prime is arbitrary. H prime is arbitrary. Now, if this H you have chosen which satisfies this condition, that is this for all alpha, then this is 0. Each term here is 0. Right? And therefore, this will be equal to 0 for arbitrary H prime. But that's in contradiction with the previous statement that B restricted to H is not degenerate. So this is the way we prove. Yeah, this is a property of the dual vector space. You can always choose a basis like this, and then it becomes very clear. I mean, you can even, so this kind of orthogonal. You've chosen a basis which is orthogonal. Okay, so these are rather. Okay, now we go to the. Is there any question here before I move to the next theorem? I have this. I think I can finish the next one also.
Did you prove this for any semi-simple algebra? This result?
Yeah. So the only any semi-simple, because the only thing we are using is non-degeneracy of B. But that was that's a way to define semi-simple. That the B is not degenerate.
No, that was another statement. We actually, do we know that being non-degenerate B leads to the semi-simple algebra?
There's a definition. So I've defined the semi-simple algebra as the ones where B is not degenerate. As I told you that in the mathematics literature, probably it varies between different books. So some books will assume, we will take as a definition that it has no non-trivial abelian ideal.
Yes,
right.
I thought that the second one is the definition and the non-degeneracy is the result of it.
Yeah, that is in some books, but in some, probably physicists would like to think like this more. But I mean, I told you right in the beginning that I'm not giving a proof.
Yeah,
you can prove it,
right.
But they're equivalent, exactly equivalent. I mean, so the statements are if and only if. If and only if this, then so it's an exactly equivalent statement. Yeah. It's not, I mean, at least you can try to do that. You can try to prove that at least one way, one of the statements, if or only if, one of the statements is easy to prove. And you can go through exactly the same thing, that if you have an abelian ideal, okay, so let's suppose the G has some abelian ideal. G, so some H is, so I'm not talking about H Cartan or something like that, no? Just some abelian ideal of G. So this is an abelian ideal. The abelian ideal means what? Ideal means that H G, H of course is 0 because it's abelian. But ideal means HG is inside H. Right? That's what it means, right? So then again, you can try to do that. Try to write down the adjoint action of H. So add H. You can try to write it in this basis, where you choose the, say, first basis is in the H, and the remaining guys are outside H. And then try to see how this add H looks like. And then you should be able to prove, in that basis again, when you try to construct the Cartan-Killing form, that it becomes 0. It is degenerate. So you can try to check that. So at least one direction you can prove more easily. Even only if it means both ways, no?
And then all the other guys on the bottom diagonal.
Yeah, right. That's right. It's, yeah. So yeah, I mean you can, so add H acting on H is of course 0, right? And this guy acting on here, it gives you back there. So there is something non-zero here, right? So this is how add H acts.
Yeah. Once we have 0 at the top diagonal.
Yeah, that's right. So this is the way. Now, so let me see, I have 15 minutes. I can try to do something here. Yeah, this we have already seen. We have already used this definition 12.6 is the same. We have already seen before. That's the definition of co-root, right? For every alpha, you define a co-root. This was we have already seen. For every alpha belonging to the roots, we define the co-root H alpha, which belongs to the H. So remember, this belong to the alpha belong to the H star dual, and H alpha is now in the Cartan itself. So we define a map from the dual vector space to the vector space. So and that map is defined simply as this: D of H alpha K is equal to alpha K for all K belonging to H. This is just defined, and that the statement is that this co-root is unique. Okay. For a given alpha, the co-root is unique. The co-root is defined with this equation. There's only meaning a unique solution to this set of these equations, because this has to be satisfied for every K, not just any K, not just one K, every K of the Cartan. This must be satisfied. And it's easy again to see. Just choose a basis. Choose a basis. This question of uniqueness is easy to see, because then what we are saying is that D of H alpha with every basis. Let's say, I don't know. What shall I call it? Some basis EI. Let's say. So EI are the basis. Basis for H. Okay. I goes from 1 up to the dimension of the Cartan. So this is going to be some number, alpha EI, which will be some number. Let's call it alpha. Let's just leave it. It's some numbers. Right hand side is some numbers. So this will give me a set of equations. I mean, since H alpha is again an element of the Cartan, I can expand the same basis, right? So I can expand now the H alpha. So H alpha I can always expand in some coefficients. Let's say H alpha I, EI, summed over I, right? Because EI is a basis, so I can always expand it. Right? So our aim is to find these guys. To determine H alpha, basically I need to find these numbers, right? These are numbers. So if I plug that in here, I'll find that it's B H alpha I, H alpha I, EI, so B, EI, EJ, let me put here J, sorry, I'll put here J, j. So B Ej Ei equal to alpha Ei for every I. And here is a sum over j, sum over j. But this is what I call Bji. So we have H alpha j Bji is equal to alpha Ei summed over j. So the matrix notation is just a dim H by dim H matrix multiplying for this H alpha, this j is the thing. So there's some j column vector. And then you take the inverse of that, multiply, so you uniquely determine these things. So, yeah, I mean, so this I can write it as some H matrix notation, H alpha times B equal to alpha, you know, with these numbers. So this is the, I mean, call this as alpha I. Sorry, this I is not labeling the root. This is labeling these numbers. So alpha I, so alpha 1, alpha 2, etc. These are numbers. Alpha, say, n dimensional space. And here you have H alpha 1, H alpha 2, up to H alpha n. And then here is this n by n matrix B. Right? And non-degeneracy basically saying that this inverse exists. So I can multiply by inverse, and that uniquely determines these numbers. So that's why it's a unique. If it was degenerate, you wouldn't be able to control any of these things. Okay, now, so the next theorem is so I mean, it always amazes me when I go through this, how almost from very little knowledge, you can construct the entire structure of the Lie algebra. This is amazing, really. So the next theorem is 12.4. So the first statement is the commutator of x alpha with x minus alpha. Okay. So we of course know that this is going to be an element of Cartan subalgebra because the result will be a zero eigenstate, right? And zero eigenstate is by definition Cartan. But now we'll be able to say specifically which Cartan element. And that turns out to be equal to B, some number, this is a number, x minus alpha. So is the killing form between the x alpha and x minus alpha times h alpha. So we knew it was a Cartan, but we are saying now that very specifically that in fact it is just a co-root. It is that co-root which was a unique element, proportional to, I mean, some number times that co-root. And the second statement was that g alpha, g minus alpha is, okay, this is not surprising, some complex. Because anyway, g alpha and g minus alpha is, I mean, you allow, at the moment we don't know whether there's only one x alpha in each, for each eigenstate. I mean, there's no degeneracy, no? There could be degeneracy, how, we don't know yet, no? Okay? So this x alpha is just one element of g alpha, but there could be independent x alphas, you know, in the same g for the same eigenstate. We are not, now this is a statement for all the g alpha, and all the g minus alpha. That it is a complex number times that. Some complex number, because anyway it's a complexified Lie algebra. So you're allowing complex numbers to multiply. Anyway, so that's the first statement. So how do we prove this? Yeah, the proof is the following. Instead of writing all the things, I'll just start proving them because maybe I will not get time to finish the whole thing. So the proof starts from this. So let's take B of x alpha, x minus alpha, that is this guy, and h, with any h. Okay. And so the idea of the proof is the following. So what are we doing? I mean, we knew anyway it's a Cartan. This part is this element, whatever appears on the right hand side is inside the Cartan, right? So and I also know that B restricted to h to the Cartan is non-degenerate, right? So if I knew how the B between this guy and all the arbitrary Cartan elements, if I know this inner product, right, then I know what it is because you know, I can always invert and find. No? So this is the reason why one is considering this. But then, remember what is that? This is nothing else by definition trace of the commutator x alpha, x minus alpha, I mean add of that times add of h. Right? This is the definition. Right? But then I can also rewrite, maybe I should continue here. Since adjoint representation is a representation, so it should satisfy the Lie algebra structure. So I can write that last equation as trace of a commutator of add x alpha with add x minus alpha times add h. Correct? Right, because this commutator is nothing else but the add adjoint of the commutator of x alpha with x minus alpha. That's what we use. And now you can use the, so what is that? Let's open it up. But this is the same as trace add, I mean the trace is cyclic, right? I can move it here, right? So this is the add h, add x alpha, commutator with add x minus alpha. Okay. I mean, so here what I have used, I mean, so what we have is trace, okay, I can bring this here, right? So trace of, let's say, x, commutated y with z, right? This is a type of thing we're looking at. So I'm just calling this as x, that is y, that is z. Huh? But that's the same, I can open this up. So you get here trace of x, y, z minus x, z, y, right? And then I write this as the following. In this term, I bring it here. By cyclicity, I move this y here. Okay. So bring the z on the last end. So move this here, put that here. But then you see that if I take z out, then you see xy minus yx. So it's the same as trace of the commutator of xy with z. So that's what I'm using. So you can just move this commutator around by using cyclicity. There's a trace property, cyclicity property. So this is x, and so it becomes a commutator of x with 1. Okay. But this I know. But this is the same as, again, using the representation property. This is the same as trace of add of h x alpha commutator, add of this guy times add x minus alpha. And this is the root. So this is proportional to x alpha with a number alpha h, right? Is the root, right? So I can take this out, that is a number. So it becomes alpha h times trace of add x alpha, add x minus alpha, which is by definition the bx alpha x minus alpha. Okay. So you get here alpha h, b x alpha x minus alpha. Okay. So we define this statement. But what is alpha h? H is this is alpha h. So how was it defined? It was simply, so this was, so I can rewrite this as alpha h was defined by the co-root equation. It was the h alpha with the, what was the equation? I forgot now. Alpha h was b of, so b, this is nothing else but the b of h alpha h, right? This guy. That is the definition of the co-root. It's just before the definition is given. Times b x alpha x minus alpha. Okay. So now just compare this. So what we have finally found that this thing is equal to that, this guy. This was my starting point, and I just moved around and got that. Now, just compare this equation and use the non-degeneracy. So yeah, in other words, I can write this again. I can simplify this again. This is a number. This is a number, right? I can put it inside here. So this is the same as B of Bx alpha, x minus alpha, times H alpha, okay, comma H. This is just a number, so I put it inside here. Okay. And now compare these two equations, this side. This should be true for all H. H was arbitrary, for all H in the Kartan, right? And since B is non-degenerate, this implies that this guy must be equal to that. Right? You see, I mean, you can just bring the two things on the same side. I mean, what does that equation is saying? That equation is saying that B of that guy, x alpha, x minus alpha, minus Bx alpha, x minus alpha, times H alpha, this whole thing with arbitrary H is equal to 0. Right? I mean, bring this on the other side. Bring this on the other side. Okay, so subtract. So, or the other way around, yes, we'll take this on the other side. So, B of this minus that, comma H. H is the same for both. Right? B is linear, bilinear, right? So this is the same as B of this with that minus B of this with that, right? The linearity property. But this has to be true for all H. Then this must be 0. That's all. Right? Here I'm using this non-degenerate. So that's how you get this expression. This expression here. So that's that. Okay. Now, second statement. Yeah, the second one. Maybe, should I stop now or continue? I'll need about 10 more minutes, 10-15 minutes more. Huh? Okay, let me just continue that. So the next statement is to prove, and this will be very interesting because this will be a very general technique. We will see. Okay. So the next step to prove is this thing that the B of H alpha with H alpha is not equal to 0. So in other words, yeah, B H alpha. Okay, I mean, it looks obvious, right? But here, I mean, we are not. You see, this is obvious if you think of B as some kind of a positive definite metric. But as we have not proven that, no. At the moment it's indefinite metric, and you know, like in the Lorentz signature, you can have light-like vectors, right? Null vectors. The light vector square with the dot product with itself is 0. So we don't know yet, no? Because we are discussing general situation, so we don't know. So this is not equal to 0. We want to prove. And this is the second point, and the third point. This is again very interesting. That, I mean, so far we have not said anything. We said that the Lie algebra G is H plus G alphas for alpha belonging to the roots, right? But we don't know whether this each of these G alphas is what's the dimension of that. There could be degeneracy, right? Although in practice we have seen both for SU2 and SU3 that it was always there was no degeneracy. For each alpha there was only one. There was always one dimensional space, not two-dimensional or three-dimensional spaces for each non-zero roots, except for alpha equal to 0, which was the Kartan. So for every non-zero, it was one dimension. So now we see that we can prove completely in general that dimension of G alpha is 1 for alpha not equal to 0, of course. For alpha not equal to 0. For alpha not equal to 0. And furthermore, what is more important, not more important, but there's another thing, is that that if alpha is a root, then, and also that dim G of n alpha, where n is any integer, is equal to 0 except for n equal to 0 or plus minus 1. That's one. For example, there cannot be 2 times the root. Which we have seen. I mean, none of the examples, SU2 and SU3, of course, is true, right? But now what we are saying is generally true.
Are all those equivalent statements? Are we saying that, or are we going to prove them?
No, they are proving each one of them separately.
They are separate statements.
Yes.
And all of this at the beginning follows from a non-degenerate.
Yeah.
Assuming just that
Yes.
gives all the results that.
Yeah. It's really amazing, yeah. And of course, the structure that we have already said, that is, has decomposed like this. I mean, Cartan algebra.
For example, we know for sure that in semi-simple algebras there are no degeneracy in roots.
Yeah.
That's a fact.
Yeah, that's right. Yeah. No, it's really mind-boggling. I mean, if you think about it, that how much you can learn from just some basic, a simple assumption, no? That B is not degenerate. Okay, so this proof this is the, I mean, so far you see we have now not used the SU2 structure at all, right? Remember, in all this SU2, SU3 example, SU2 was trivial, there was only one. For each root, we had an SU2 subalgebra, right? And so far, in all this discussion, we have not used it, but now we are going to use it. And this will be a very standard trick that we will be using. So the idea is the following. So let's suppose there is a root. So alpha is already, so for this discussion, for this discussion, let's see. Yeah, for this discussion, so let's do the following. Alpha is a root anyway, because otherwise there's not even discussion about this question, right? So I'm assuming the alpha is a root, and H alpha is a co-root, okay? But now let's take some beta, which is another root, which is not alpha itself, it's some other root. Then consider this chain. So we consider a chain of roots and root spaces or root vectors. Okay, and we take this subspace V, which is this subspace of the full G. So this is contained in full G. Okay, but this subspace I define like this: N belonging to integers Z, G of beta plus N alpha. Okay. I mean, when it exists. Okay. Otherwise, it's an empty set. If this is not a root, it's not one of the roots in your set, then this will be an empty set. Otherwise, okay. So just consider this place. Now, the important point is the following: that if you look at this, then and look at these 3 generators: X alpha, X minus. So first, let's look at H alpha. H alpha clearly takes V to V, right? That's clear because each of these spaces has eigenspaces of the Cartan. So Cartan will keep a state here to a state here itself, right? It won't take you somewhere else. So this is clear. But what is more non-trivial is if you look at X alpha, action of X alpha, what is it going to do? It will take one of these beta plus N alpha. So add X alpha. These are all, I'm applying add X alpha on this space. Then it will take G beta plus N alpha to G beta plus N plus 1 alpha. Correct? Because they just add up. The eigenvalues add up. Right? And the same thing with the plus or minus. Plus or minus, it will be plus or minus. Okay? And furthermore, we also know that X alpha with X minus alpha is H alpha. Some number times H alpha, proportional to H alpha. This is a number. Right? Okay. So then we are saying that this space is invariant under these three actions. X alpha, X minus alpha, and H. This is invariant. So I can talk about I can compute the trace of H. I can compute the trace of add H alpha, but not take the trace over the full G. No, just in this V subspace. This I can do because as far as these three, I mean H for H, I mean I just every space here is invariant as far as H is concerned. But I'm including all of these spaces because I also want, and you will see why, I also want this space to be invariant under X plus and X minus alpha. If I was only interested in add H alpha, I mean just this statement, it would have been enough to just focus on just one of them, beta plus and alpha. And it will just give me, what will it give me? It will give me the eigenvalue, which will be H, which will be, what is the eigenvalue? I think it will be beta plus n alpha evaluated at H alpha, right? Or H alpha, evaluated at H alpha. H alpha is just one of the elements. That will be eigenvalue and times the dimension of this space. Right? Is that agree? Because I mean, this may have some dimension. It could have some not just one. It could be any dimension. But every time add H alpha acts on any of these states, it gives me a number being this number, the eigenvalue, times the same state. Right? So this will become this number. This operator will become this number times an identity matrix. Okay. That's correct. I mean, what I'm saying is that if you take any state, X belonging to this state, this space, how does add H alpha act? Add H alpha acting on X will be simply this number. This is a number times X. True? For anything, for any element here. That means acting on this space, add H alpha is proportional to identity. And the proportionality constant being this. So it will be this number times identity. And then when I take the trace of the identity in this space, it will just count what is the dimension of that space. Right? So that's why it's a dimensional generator. So this number times that. That would be fine. But the reason why I want to look at this big space is because I also want it to be invariant under X plus and X minus alpha. And you see the reason why. Because now I can use, so if I evaluate this in this big space, not in the small space. This is a small space, right? But in this big space, I take the trace. Then, in this big space, so if I take the trace over V of add H alpha, then I can use this definition, this property that X alpha, X minus alpha, this is that previous theorem, previous statement which we have proved. I just erased it, which was X alpha, X minus alpha was equal to B X alpha, X minus alpha times H alpha. Right? So, sorry, this alpha. So then add H alpha can be expressed as so let me just multiply this by B X alpha, X minus alpha. Okay, X minus alpha. I multiply that, then this guy is nothing else but X alpha, X minus alpha commutative. Okay? So this I can write, this is the same as trace V of add X alpha commutated with X minus alpha. This will have no meaning if I had restricted to the space of an individual space. I mean, that expression will have no meaning. Or at least I cannot make use of it in any significant way. Okay? Because the X minus alpha and X alpha takes this space to another space. Right? But now we are in this big space V, and we have already proven that these guys, I mean, the V is invariant under this action. So each individually, add X alpha and add X minus alpha, takes a state in V and brings it back to the V. Right? in that case, then I can, of course, write this as trace V of add x alpha, add x minus alpha, commutative, right? And it makes sense because this is all, each one of them is acting within the V. So I can write each of them as a matrix of the dimension of the V. Right? Suppose V is some m dimension. Huh? This V is this big V is some total dimension is m. Then I can represent each of them inside this space as some m by m matrices. Right?
I don't want to miss that.
Add itself is a big thing, right? Add is good, acting on everything. But here I'm still, this is a subspace of G. So a joint is of course a dim G by dim G matrix. But because it is, this space is invariant under this action, right? I can write this action here as a m by m matrix, where m is a dimension of V. And once I can write it as a m by m matrix, then this trace of the commutator is 0, right? Trace of the commutator is 0. Because this is a matrix, say m1 times m2. So it's m1 times m2 minus m2 times m1 of the trace. But trace is cyclic, so it is 0. So therefore, this is 0. So this is an important point. But now I can, okay, that's on the one side. But now I can compute this directly, right? I can compute this directly by it's just this quantity, right? We already, this is for this particular space, but I have to now just sum over all these spaces. So that thing just becomes, so over the V, it just becomes this summed over M. That's this. Okay. Okay, so, but now look at this here.
Should we write H alpha in that expression?
Which expression? Here.
Yes.
Yeah, because this is evaluated, I mean, add, in general, add H.
It means evaluated X.
Huh? Yeah, it's evaluated at H alpha, for H alpha. H alpha is a particular element. Yeah. Okay. So now if you look at this here, this expression is what? This is beta H alpha plus n alpha H alpha. Right? And this is a linear thing. So this expression is that. And therefore I can write this as what is the B of beta of H alpha? That is nothing else but beta of H beta H alpha. That's the first term. And this one is plus n H B of H alpha H alpha. So that's the statement. Now, so I said, okay, we take beta in delta, right? So what was given? You gave me, or somebody gave me alpha. Alpha is an element. Now I know there must exist some beta in the set of all the roots, such that B of H alpha, H beta is not equal to 0. So I choose a beta in such a way that this is not 0. So choose, I mean, now I'm specializing for a particular, so far this argument is for arbitrary beta, right? But now I specialize to the case where choose a beta such that H alpha H beta is not 0. This is possible, why? Because we have already proven that this dual vectors span the entire space, right? So I can always find some H beta such that this is not equal to, and the fact that B is not degenerate with to the Cartan space. So I can always find a beta like this. That is what I was using. And then you see, so therefore this is not 0. This guy, first guy is not 0 in the expression. So I'm just computing this object, a trace of add H alpha. So this is not 0. So how can it be? On the other hand, I know the whole, after taking all the sum, it should be 0. So the only way it can become 0 is this part somehow cancels that, right? But for this part to cancel, I mean, this better be non-zero. You see, if suppose this was 0, then each of these, no matter what the value of n is, each of these terms is 0, but this I know is not 0, because I've chosen beta like that, right? So therefore, you conclude that this implies that, I mean, the only hope of making it 0 is if this is not 0, right? So that proves the first statement, that this is not 0. So in other words, H alpha is not a null vector. You know, like in the Lorentzian signature, you have null vectors, no? So what we are saying in H alpha is not null. That's so far that. Huh? And yeah. And I should say, yeah, yeah. I mean, I should also mention here that, I mean, this is of course, this term is multiplying dim dimension of that. So one might have said that perhaps these guys are 0. But certainly for n equal to 0, this is just dim g beta. That is certainly not 0, because I'm saying that there exists a root beta. Right? So at least that dim g is at least 1. Perhaps could be more, but at least 1. No? So this is not 0. For n equal to 0, it's not 0. Dim g beta is not equal to 0. So that's why the only way to satisfy this condition is if this is not 0. If this is 0, then there's no way. You cannot satisfy this equation. So that's why it concludes. Okay, now you apply the same thing now. Now, this kind of an argument is, okay, maybe I will go to the next one tomorrow. Tomorrow is Thursday. Yeah, tomorrow I have it. Yeah. Let me do that but I just want to stress that this method will be used again and again. This method of writing a chain, these are called a chain group vectors. So for any alpha, you write a chain which is called alpha chain, starting from beta. So this is called alpha chain, starting from beta. So I take a beta, some beta and some alpha, and I can write an alpha chain. And what is the importance of that is that under this SU2, you know, at the moment we have not proven this it's almost like SU2, because we have this relation, right? This exact, and we have the relation H alpha with X plus or minus alpha is simply alpha H alpha, okay, times X plus minus alpha, right? It is exactly like SU2. You can normalize them. You can divide suitably by various these numbers, etc., to bring it exactly like SU2. Right? This was the plus and minus were the raising and lowering operators of the SU2. Sigma plus and sigma minus. You see, think of this as sigma 3 and this sigma plus minus. Sigma 3 with sigma plus minus gives you sigma plus minus back, right? If you're worried about this number, I can divide by this number, no? And redefine my new H alpha. Then you just get that. And finally, the sigma plus sigma minus gives you, again, some number times sigma 3. But these numbers you can renormalize. You can redefine these things to exactly map to sigma plus, sigma minus, and sigma 3. So the upshot is that for every root alpha, we already we already know from this structure that this is not. This gives you an SU2 subalgebra. And what we are doing here by looking at these chains is just taking this full big Lie algebra and decomposing that in terms of representations of this particular SU2 subalgebra. That's what one is doing, right? We did that for SU3. Remember, SU3 we had if you take alpha 1, there was an SU2 subalgebra. There were two doublets, one triplet, and one singlet, right? That's exactly what one is doing. One is just taking this thing. This SU2 acts on that. Right? And this statement of the total trace is 0 is just that statement that that in any irreducible representation of SU2, the J3 quantum number, sigma 3 quantum number comes with there's a symmetry. For every plus n, there's a minus n. So when you take the trace, it vanishes, right? So that's exactly the reason why this is vanishing here. So these are S2 subalgebras. Yeah.
And the further statement that in G alpha is 1, we are saying that we can decompose any kind of the algebra into smaller irreducible representations of SU2. Right? We have one direction to go up and down,
That's right.
as we do in
Yeah.
SU2. So all kinds of any imaginable Lie algebra can be in the end distractible.
Yeah, that's right. Yeah, that's exactly right. Of course, one is using non-degeneracy of B. In every step, they have been using
for every semester.
Every semester. Okay, I better now go. So we will continue that. So the next steps are again always going to be using some suitably chosen chain. So we'll just choose various suitable, what is suitable for the purpose. We'll choose various chains and come to various conclusions. This is the main idea.